Hello, greeting to you all. My name is A.Malik and I am from CHE Department D section and I am here to display my Tech Talk topic on computer systems architecture. The topic name is Virtual Memory Issues of Implementation. Introduction. Virtual memory issues of implementation. The definition is a memory management technique using virtual addresses allows execution of processes larger than physical memory, provides isolation, protection, and flexibility. Widely used in modern operating systems. Windows, Linux, Mac are just examples of the operating systems. Focus. Challenges in designing and implementing virtual memory, address translation, and page table management. Map virtual addresses to physical frames using page tables. Single level tables are impractical for large address space. Multi level, inverted, or hash page tables reduce overhead. Requires MMU, which stands for Memory Management Unit support. Goal: minimize lookup time and table memory usage. Page selection, page size selection. Smaller page is equal to less internal fragmentation but more table entries. Larger page is equal to fewer entries but higher fragmentation risk. Page size affect input or output performance and TLB efficiency. Many operating systems support multiple page size, example 4 KB, 2 MB, like that. Trade-off is a key for optimal memory utilization. Page replacement policies used when physical memory is full. Common algorithms like FIFO, LRU, LFU, clock. True LRU is expensive approximation are used. Replacement impact page fall frequency. Good policies minimize input output operations. Translation look aside buffer TLB. A small cache storing recent page table entries reduces address translation time drastically. Multi-level TLBs used in modern CPUs issue miss penalty flushes on context switch. Efficient TLB design critical for performance. Page fault handling occurs when a required page is not in a RAM. Operating systems load the page from disk or swap space. Page faults are expensive. MS level latency. Handler manage dirty pages and replacement. Goal: reduces frequency and impact of page fault. Demands paging and prefetching. Demand paging, load page only when accessed. Prefetching, predict and load page in advance. Reduce startup time but may cause overhead. Accuracy of prediction affects performance, balance memory usage, and response time. Thrashing and working set model. Thrashing: CPU spends more time paging than executing, caused by insufficient memory allocation. Working set of actively used pages. Dynamic memory allocation help avoid thrashing. Monitoring workload pattern is essential. Memory protection and isolation prevent processors from accessing unauthorized memory. Use access control bit R or W or X in page table entries. Supports sandboxing and security features. Hardware enforced via MMU. Protects against crashes and malicious behavior. Swapping and storage management. When memory is full, inactive pages are swapped to disk. Requires a dedicated swap area or paging file. Disk performance is a major bottleneck. Smart disk scheduling improve performance. Some operating systems use compression before swapping. Shared memory and copy on write, in short form COW. Shared memory allows fast IPC between processes. Copy on write. Pages shared until a write occurs. Reduces memory duplication during fork calls. Requires fine-grained page-level protection. Widely used in modern operating systems for optimization. NUMA and hardware operating systems cooperations. NUMA systems memory access time depends on CPU node. OS systems must manage thread and data placement. Hardware MMU TLB and operating systems must work closely. Features huge pages, ASLR, virtualization support, balances, flexibility, security, and speed. Virtual memory in virtualization. Hypervisors use nesting pages EPT, NPT for VMS, add extra translation layers, guest to host to physical. Hardware acceleration improves VM performance. Complex TLB management for multiple address spaces. VM snapshots and migration depends on efficient paging. Caching and virtual memory interaction. CPU caches operate with physical addresses. Synonyms or aliasing issue arise with virtual indexing. Cache coloring reduces conflict misses. Require careful operating system hardware synchronization. Cache and virtual memory design deeply interlinked. Memory mapped files. Map files directly into virtual address space. Allow files input or output via simple memory access. Reduces, reduces system calls and speed up operations. Use for shared libraries and large dataset access. Requires page fault driven loading of file pages. Real-time systems and virtual memory. Virtual memory adds latency in real-time systems. Page fault are unpredictable, affecting deadlines. Real-time operating systems use locked memory pages. TLB and cache must be carefully managed. trade-off between flexibility and predictability. Security challenges in virtual memory. Address space layout randomization in short form ASLR prevents exploits. Memory protection prevents buffer overflows. Side channel attack. Spectra meltdown exploit caching. Virtualization add more security layers. Continuous patching needed for modern threats. Thank you.